You're seeing them everywhere now, right? These absolutely giant, kind of graceful towers spinning on the horizon. They're obviously a huge part of our energy future, but let's be honest. How many of us really know how they work? And maybe more importantly, how does something that's literally designed to catch the wind survive a direct hit from a hurricane? Yeah, let's get into that. So first off, why the huge push for wind? Well, beyond the whole climate conversation, it really just comes down to simple math. Our fossil fuels aren't going to last forever. Now look, this forecast is from back in 2008, so you can bet the exact dates have shifted around a bit. But the fundamental point? It's sharper than ever. The clock is absolutely ticking, and that reality is what makes mastering renewables like wind so incredibly urgent. Okay, so with that urgency kind of lighting a fire under us, let's dig into the beautiful science of this. How do we turn something as simple and invisible as a breeze into the actual electricity that powers our lives? It's this amazing mix of elegant physics and some seriously brilliant engineering. Now, you might think a turbine works just like an old-school Dutch windmill. The wind just pushes the blades around. That's called the drag principle. And honestly, it's surprisingly inefficient. Today's turbines use something way more sophisticated, called the lift principle. It is the exact same force that makes an airplane fly. The blade is shaped like a wing, so as air zips over it, it creates this zone of low pressure on one side that literally pulls the blade forward. It captures over 3 times more energy from the very same gust of wind. It's just so much smarter. So here's how that lift turns into the light in your house. Those incredible blades, they capture the wind's kinetic energy, which gets the central hub, the rotor, spinning. That spinning motion, that's pure mechanical power. It gets channeled into a generator, which is basically just a massive alternator. And that's what converts the rotation into electrical energy. From there, boom, that clean power is sent off to the grid, ready to charge your phone or light up your entire city. All right, so a turbine's whole job, its entire reason for being, is to catch the wind. But what happens when that wind becomes the enemy? When a nice breeze turns into a gale-force storm. How does this finely tuned machine survive forces that can literally tear buildings apart? Well, the first part of the answer is that these things are engineered to be unbelievably tough. I mean, international standards require them to handle sustained winds over 112 miles per hour. For perspective, that is solid Category 2 hurricane strength. They are absolute marvels of resilient design. But just being strong isn't enough. They also have to be smart. And that intelligence is all programmed into something called the power curve. And don't think of this as some boring technical chart. It's really the turbine's brain. It's a set of automatic survival instincts for pretty much any wind condition you can imagine. It all starts at what's called the cut-in speed. All it takes is a wind of just 6 to 9 miles per hour. I mean, that's barely a breeze. And the turbine comes to life. The blades start to turn, and it starts sending its first little watts of power out to the grid. Then, as the wind gets stronger, the power output just climbs and climbs until it hits this perfect sweet spot, right around 30 miles per hour. That's the rated speed. That's when the turbine is in its prime, just humming along, generating the maximum amount of electricity it was designed for, all safe and sound. But here's the crucial part. This is where the genius really kicks in. When winds start surging past 55 miles per hour, the self-preservation protocol takes over. At this cutout speed, the turbine's brain basically says, okay, safety is way more important than making power right now. And it starts a graceful automatic shutdown to protect itself from all that stress. And the process is just so elegant. There's a little sensor, an anemometer, that's constantly measuring wind speed. The second it detects dangerous conditions, the blades feather. They pivot 90 degrees, turning their thinnest edge into the wind. It's kind of like turning a knife's sharp edge into the wind instead of its big flat side. The force just spills right past them. And then the turbine just waits. It monitors the storm, and as soon as the wind drops to a safe level, it automatically starts right back up again. And look, this isn't just theory. Back in 2017, the Block Island Wind Farm, America's very first offshore installation, got hit by a storm with gusts over 70 miles per hour. The system worked perfectly. The turbine shut down, they rode out the storm without a single scratch, and then they powered right back up when it was over. It was the perfect real-world test of this incredible engineering. That success at Block Island really highlights the next big question. Where should we even build these things? And the choice pretty much comes down to 2 places, on land or out at sea. And as you'd expect, there are some pretty clear trade-offs. Onshore, it's cheaper and it's way easier for construction and maintenance. But offshore? Well, offshore has a game-changing advantage, the wind itself. Out at sea, the winds are so much stronger and way more consistent because there are no hills or buildings or anything to block them. That leads to a higher capacity factor, which is just a fancy way of saying the turbines are generating power more of the time. That efficiency, plus the fact that they don't have a big visual impact on communities, makes the ocean incredibly appealing. It's because of all those advantages that the world is making this massive bet on offshore wind. I mean, think about it. More consistent power. You can build much, much larger turbines, and there's minimal disruption to people. It's a powerful combo. You've got projects like the absolutely colossal Dogger Bank wind farm in the UK. That's going to power up to 6 million homes and create this whole new clean energy economy for coastal areas. But here's the thing. As amazing as today's tech is, we are really only just scratching the surface. The next great leap for wind power is to move even farther from the shore, into a future that is, quite literally, floating. So up until now, offshore turbines had to be physically fixed to the seabed and only in pretty shallow water. The game changer is floating wind farms. By mounting these turbines on floating platforms that are tethered to the seabed with massive anchors, we can suddenly unlock these vast, deep water areas of the ocean, where the winds just happen to be the strongest and most reliable on the entire planet. Okay, the next big idea is to completely evolve beyond thinking of wind farms as just single power plants for one country. These offshore hybrid assets, or OHAs, will connect whole clusters of wind farms, not just to one grid, but to several. You're basically creating an international clean energy supergrid where different nations can share power in real time, balancing everything out across borders. And maybe the most ambitious vision of all is the energy island. I want you to picture these giant man-made hubs built way out at sea. They'll act as central connection points for enormous wind farms, but they'll also be factories that use any excess wind power to produce green hydrogen. So you're effectively bottling the wind's energy to be used whenever and wherever it's needed. It's incredible stuff. So you go from a single blade using the same physics as an airplane wing, all the way to floating energy islands that can power entire continents. The evolution of wind power is just accelerating like crazy, and it leaves you with this really fascinating thought. As this technology keeps pushing out into deeper waters and connecting our world in brand new ways, what other unimagined energy horizons is it going to unlock for all of us?